Welcome, everyone, to an impromptu triple observatory
You hearing me?
broadcast for 25 August
Or
2026. Tonight, the Allan I Carswell Observatory is joined by the Harry Bayley Observatory in Barbados to enjoy a talk by the Barbados astronomer and current Killarney Parks Observatory astronomer in residence, Seneca Smith. Seneca is giving a talk titled The Stellar Life Cycle, and the images are coming to you from all three observatories across the world. Can you tell which observatory is which? Let's go live to the talk by Seneca now.
all right, good night, everyone. Can you hear me?
We can hear
Fantastic.
you great.
Thank you very much, Bruce, for your kind introduction and for overselling my skills on the cello. Tonight, we're not here to talk about the cello, we're here to talk about stars. So, what I'm going to do is I'm going to talk us through a little bit about the life cycle of stars. We're going to talk about where stars live, where they're born, where they die, and of course, live lives. They're active. No, it is a really special night. We're really ambitious, really collaborative, collaborating between three different observatories. So we're going to be seeing and image taken by three different sites here at Killarney, at ICO in Toronto, and at the Harry Bayley Observatory, weather permitting, of course. The one constant in astronomy is that we're always subject to the weather. So we're going to do our absolute best. That said, let's get started. I want to start by talking about where stars live. The image that's on screen is of a galaxy. Does anybody have a quick, short definition of a galaxy? A bunch of stars is a fantastic definition of a galaxy. You're very welcome. So, a brief definition of a galaxy is a collection of stars. You could add to that they're gravitationally bound to each other, so they're interacting through the force of gravity. You could go a little bit further than that. You could say that it's not just the stars themselves, but the gases around them and the dust around them, any planets that are around those stars. So galaxies end up being more complicated than just stars. Welcome to the guests that are just joining us, who I'm going to direct away from the deck and around this way. Oh, this way, around this way. Thank you very much. Right, so galaxies, really interesting, really complicated, involving not just stars, but also dust interacting with those stars, all interacting, bound together by gravity. At one point, there was one known galaxy. Does anyone know what that was? The Milky Way. So on a clear night that has a little less light pollution from the moon, you can see the Milky Way really clearly in Killarney across the sky as a streak. Usually to the naked eye, it looks like a band of white cloudiness in the sky. In fact, the word galaxy, does anyone know what's cognate? What words come to mind when we think of galaxy? What do we think the root might be? Hmm, not quite. We're a little too sophisticated. The root lactose, lack anything, milk. So the word galaxy actually shares a root with the word for milk because of its milky appearance across the sky. And when there was only one known galaxy, that's just what it was, this milky band across the sky. We now know that there are far more than one galaxy. In fact, we think that there are between 200 billion and 2 trillion galaxies in the observable universe. So, far more than one, I think. I mentioned that galaxies are complicated. There's a lot going on, but they're also dynamical systems. They're going through a lot of changes. They evolve over time. And they're a very diverse population of elements of our universe. Galaxies vary in terms of shape. There are spiral galaxies like the one you see on screen, and I'll get into a little more detail about the one we're seeing here. It's not just a spiral galaxy. There are elliptical galaxies that are more rounded in shape. There's something in between called a lenticular galaxy, different shapes of galaxies. They vary greatly in size as well. Our own Milky Way is about 100,000 light years across. That means if you were to go to one end of the Milky Way and turn on a flashlight, that beam of light would take 100,000 years to get to the other side of the Milky Way. Long time. Some galaxies are a lot smaller than that, though. Some dwarf galaxies are as small as 3,000 light years. So it would only take a paltry 3,000 years for that beam of light to get across the galaxy. But some galaxies are much larger, as large as 300,000 light years. so about 3 times as far across as our Milky Way. Galaxies also have all sorts of different colors. We're going to see in a minute what the color of a star means, but if we look at the color composition of a galaxy, we can learn things about its age, we can learn about whether it's forming stars, we can learn about all sorts of stuff about a galaxy from its colors. So, shapes, sizes, colors, galaxies form a diverse population of objects in our universe. Now, the object that we're looking at on screen is cataloged as M51, exciting name, colloquially called by its friends the Whirlpool Galaxy. Now, the Whirlpool Galaxy is interesting because it's not by its lonesome. The Whirlpool Galaxy is interacting with another galaxy in space. I mentioned that galaxies are gravitationally bound within themselves, but galaxies also exist in larger populations of galaxies called clusters. Those clusters can have interactions between the galaxies that make them up, and sometimes that's destructive to the shape of the galaxy. So over time, we see galaxies merge and change in shape as they interact with each other under gravity. Is that a question? Nope, that's getting someone else's attention. All right. Any questions about galaxies? Great. So, if we think about galaxies as sort of islands of stars in the cosmos, and I think that's a reasonable way to think about it. I maybe think that because I'm from an island, and islands are my default way of thinking. But if we think of galaxies as islands of stars, then a globular cluster might be a city of stars. Globular clusters are collections of stars that are between tens and hundreds of light years across. Remember, galaxies are thousands of light years to hundreds of thousands of light years across. So this globular cluster is much, much smaller. It has fewer stars, from tens of thousands to millions of stars. But because the globular cluster is so much smaller, even though it has fewer stars, the average distance between stars is much smaller. Does anybody know offhand how close the closest star to the Earth is? No, we actually had the answer earlier. 8 light minutes. What's the closest star to the Earth? The Sun. All right, I got you there. So, yeah, it's about 8 minutes, 20 seconds-ish. Very close. Let's ask a different question then. The closest star to the Sun, how far away is that? We just had the answer. About 4 light years. So it would take a beam of light about 4 years to go between the Sun and its nearest neighbor. In globular clusters, stars are much, much closer. In fact, the average distance between stars in a globular cluster is about a third of a light year. So about 1/13 of the distance between the Sun and its nearest star. If we were around a star in a globular cluster, we'd experience a lot more light. There would be a lot more stars closer to us, giving off more light, more radiation. Globular clusters are found in most galaxies. Our own Milky Way has over 150 known globular clusters. The formation of globular clusters is not totally clear. There are a couple of different ideas about how they form. One of those includes potentially that they were small captured fragments of galaxies or the cores of galaxies. In fact, one of the globular clusters that's sort of on the edge of the Milky Way is thought to have been the core of a galaxy that didn't really survive its interaction with the Milky Way. What we do know about globular clusters is that many of them are very, very old, billions of years old, and they contain stars of different ages. So globular clusters, they're old, they're relatively small compared to the galaxy, but they contain many, many stars in a very dense area. So I think we just had an image of a globular cluster. If we could get that back.
Trying.
Thank you. Oh, I should mention, our first contribution to the images, the Whirlpool Galaxy was taken right here at the Killarney Provincial Park Observatory. Using the telescope behind you, I believe.
Yep.
Yep.
David, if you can hear us,
While we wait, does anyone know any great jokes about globular clusters? They're like a star retirement home. That is actually a great joke about globular clusters. Kudos to you.
Who said that?
Unexpected.
We're almost there, Seneca.
Sure. So I believe the image of the M22 globular cluster we're going to see is coming from the Harry Bayley Observatory. Is that right, Bruce?
It will be.
It will be.
They're almost there.
See, if I had my cello, I'd play elevator music.
Can you sing, Seneca?
Can I sing? No. Especially not no. If I sound a little bit hoarse, it's because I've been oohing and eyeing at this amazing park for the last couple of days. Everyone else, I'm sure, has had a similar reaction. Yes, this place is gorgeous, isn't it? Yeah. In fact, I almost feel guilty breaking the pristine silence with this voice for this presentation. I'm sure no one is from as far away as our closest neighbor star, 4 light years away. Does anyone think they maybe joined us from the furthest away tonight? No one hazard to. Are we all from Toronto?
In the meantime, we're just going to put on some galaxy images also that we have from ACO, from Allan I Carswell Observatory.
Okay, so we're going to share some images of galaxies that we have from the Allan I Carswell Observatory at York University in Toronto. As I said, this is an ambitious coordination effort. We're working with 3 different sites and weather conditions in 3 different locales, really across this part of the world.
Let's see if we can get a Harry Bayley again.
The question was, where in Barbados is the observatory located? It's in Christchurch in the southern part of the island. Near-ish to Bridgetown, near enough to be frustrating at times with light pollution.
But can you...
The question was, how much of an issue are satellites nowadays? Not yet a massive problem for optical observations for us in Barbados. We often get from our amateur photography work, because in the Astronomical Society we have a lot of amateur astrophotographers, and quite often we'll have images that have, a streak of light that turns out to be a satellite, but it doesn't often impact our more serious imaging. Yet, fingers crossed. Satellites, I think, might be more of a problem for radio astronomy before they're a problem for optical astronomy. Looking with our telescopes, we're not terribly impacted by them so far. All right, so it looks like we have our feed of M22, another fantastic name for a stellar object. I should let you know, when you hear M and then a number NGC and then a number, that's referring to some kind of stellar or galactic catalog. It's not always feasible to give every astronomical object a unique name, so often there will be a catalog, code, and a number to go with that. What we're looking at here, I believe, is the M22 globular cluster from the Harry Bayley Observatory. Thank you very much, David. Our President David Marshall is at the Harry Bayley Observatory right now, imaging for us. Hi, David.
They're quiet.
Hi, Seneca.
Great. Okay, so thank you for the image of the globular cluster. So we have islands of stars in the form of galaxies. We have cities of stars, but we're here to talk about stars. So I asked for a quick definition of a galaxy. Can I get a quick definition of a star? Flaming bag of gas is a decent start. Great ball of gas is what might be said otherwise. Burning is a word that's often used. Gas is a word that's often used. And it's not a bad start. We can get a little bit more precise with that. Let's start with gas. Stars aren't technically gas. They're another state of matter called plasma, which is similar in a lot of ways to a gas, but it has a lot more energy. You might think of it as angry gas. Uh, Stars aren't quite burning either. Stars are undergoing a process called nuclear fusion. Burning is a chemical process that involves adding oxygen to a material in a process called combustion. Nuclear fusion is a physical process that happens in the cores of elements, in their nuclei. What's happening in stars is that one element is being transformed into another. It's not chemistry, it's fundamental physics. So the fusion that's being done in stars transforms hydrogen into helium, helium into heavier elements. What did we say was the closest star to the Earth? The sun. Great. We're still with us. So the sun is actually how we know quite a lot about stars, but not every star is exactly like the sun. So by doing observations of other stars, we learn a lot more about physics, a lot more about astronomy, and how the universe around us works. So I mentioned that stars are doing nuclear fusion. The other process that's really dominating what happens in a star is gravity. Stars have a lot of mass, just so much, an unimaginable amount of material that's pulling in towards itself under gravity. Fusion is counteracting that. Fusion is causing the star to expand as gravity causes it to contract. Meanwhile, hydrogen is being turned into heavier elements, and depending on the mass of the star, that will determine the rate of fusion, how quickly that hydrogen is combined. As you can imagine, if you have a lot more material that's producing a lot more gravity, it's compressing the star a lot more, and that increases the rate of nuclear fusion. What that means is that different stars of different masses have different properties. Larger mass stars are brighter, they burn hotter, but they live shorter lives. Smaller stars, less massive, they burn through their hydrogen a lot slower, they live a lot longer life. The rate at which stars burn through hydrogen also determines their temperature, which in turn determines their color. So we have different masses, different rates of fusion, different color. We're finding that stars are just as diverse a population of objects in the night sky as galaxies are. A great example of this is what's on screen now. I will call it the star Albireo, because the star Albireo is the head of Cygnus, the swan, the constellation. With a powerful telescope like we have here at the Killarney Provincial Park Observatory, we're able to see Albireo more than one object in the sky. And in fact, this object that we're seeing right now is being produced right behind you on our telescope. So, Albireo, it looks like one object on the sky. It's actually two. It's really two. We have a brighter yellow object, a dimmer, it should be bluish, but we have a lot of, into the atmosphere. A brighter yellow object, it turns out, is likely actually more than one star as well. And one of the objects that makes up that star is actually itself probably more than one star. In fact, if you look up at the sky, about half of the objects of light that you see, about half of the stars you see, are in multiple star systems, or are at least two objects of light. The interesting thing about one of the many interesting things about Albireo is that it's not clear whether those stars are gravitationally bound to each other or whether one is in the foreground and one is in the background. One could be far, far distant beyond the other. That's still an issue of debate amongst astronomers. What we do know is that when we look up and see one bright object, it's actually made up of multiple in the Albireo. So, I mentioned that stars are combining hydrogen. In fact, stars are almost entirely made up of hydrogen. And that means that they can only form what? Hydrogen. Good. If you'd said helium, I would have been a little bit confused. Yeah, so stars form in regions that have a lot of hydrogen. Most of the matter of galaxies, fortunately, turns out to be hydrogen. In fact, about 75%, about three-quarters of the mass of galaxies is hydrogen gas. So stars have ample material from which to form, but they don't just form anywhere. Stars form in areas of space called nebulae. Nebulae are essentially clouds of hydrogen gas in space. Well, clouds of gas, more generally speaking, in space. They're, as I said, mostly hydrogen. And what we see when we look at nebulae that contain hydrogen is that they often contain a large number of very bright, very hot stars. Now, what do we say was true about larger, hotter, brighter stars? They die faster, exactly. So if you're seeing somewhere where there are lots of bright, hot stars, those stars have to be young because those stars, simply put, don't get old. So when we look at nebulae, we often see these high concentrations of bright, young, large, hot stars. As part of the clues that lead us to conclude that stars are in fact being born in these nebulae made up of gas. I think we can get an image, I hope, of the Trifid Nebula.
Working on it.
Working on it. Fantastic. So the Trifid Nebula is one of these regions of star formation. It's what we call an H2 region. That's the letter H followed by the Roman numeral 2. Looks like HII or a very excited hi. And hi is appropriate. It's where stars first say hello. What H2 is, it's excited hydrogen. It's hydrogen gas, not this. It's hydrogen gas that has been supplied with energy. And then one of the electrons, well, the electron in the hydrogen gas is promoted or excited to a higher energy level, and it gives off light. These H2 regions are warmed by the formation of stars within them. So as stars are born, they go through the process of nuclear fusion. They heat up the gas around them, converting ordinary hydrogen into H2. And the H2 regions, oh, that's gorgeous. So this is the Trifid Nebula, one of the H2 regions in space. This is an area where stars are being born. Notice the beautiful coloration. Reds and pinks are very typical of hydrogen in space. It is the most abundant color, so a lot of nebula that you, sorry, it's the most abundant material in space, so a lot of nebulae that you see will be red in color. But there are also these gorgeous blues. And blues can be a combination of things. Sometimes it's a result of helium gas, but quite often, blue is a reflection of the starlight being produced within the nebula itself. So as these very hot, very bright, often very blue stars are born, they produce their own light, and that light is reflected off some of the dust and some of the gas in the nebula. So we see the red of the hydrogen, the blue of the stars reflected back. So that's where stars are born. H2 regions, nebulae in space. Nebulae don't last forever though. Eventually, as a lot of the hydrogen is used up, as stars are produced, as stars go through their lives, a lot of the gas is used up or dispersed. What's left is the stars that were born there. Often, this forms what's called an open cluster of stars. Open clusters are, as I said, what eventually is left behind when the gas of the nebula disperses, and the deaths of stars and other processes blow away a lot of the material that's there, leaving behind just the bare stars themselves. Open clusters tend to have between a few tens, so 10 to 30, all the way up to thousands of stars in them. So that's far fewer stars in globular clusters, which we said start at about 10,000 stars. So just a few thousand stars in an open cluster. These stars are typically loosely bound together by gravity. So there's some gravitational interaction, some pushing and pulling, well, some mutual pulling of these stars on each other under gravity, but they're not totally bound together by gravity. They're often moving apart. And so even the open cluster doesn't last forever as these stars find their own way in space. Open clusters tend to be found in younger galaxies, spiral galaxies, as well as in irregular galaxies. Now, irregular galaxies, I mentioned that we were going to come back to the interaction between the two galaxies. We saw earlier the Whirlpool galaxy and its neighbor. The inevitable result of that interaction is what's called an irregular galaxy, a galaxy whose shape is not part of the typical process of galaxies' lives. And these galaxies are one place where we often find open clusters, places where we have active star formation and nebulae that are just getting through the majority of their hydrogen supply. I'm hoping we'll get to see open cluster M11. Now, we had a fantastic joke a minute ago about globular clusters. Is it too much to expect a great joke about open clusters? Oh. Do we have another headset? So that additional comment was, if the globular cluster is a star retirement home, then the open cluster is like a star high school. They're all hot and young. Oh, okay. Moving swiftly along.
Just a second.
Sure. The open cluster that we're hoping to see in a second, as with promises, is the Wild Duck Nebula. It's reportedly named for its appearance resembling a flock of wild ducks. Now, personally, I don't see it. If you see it, you have to tell me. But that's what they tell us. The open cluster, the Wild Duck Cluster, looks like a flock of wild ducks in flight. It's about 6,000 light years away. So, here we go. This is the Wild Duck Nebula. Sorry, Wild Duck Open Cluster. It's gone again.
Hold on.
It will be back.
Just a second.
Yep. It's back. Does anybody see it? No, I'm told that the head of the formation, and I'm going to step slightly in front of the projector here, is down in this area, and there's like a V. So offended was Bruce by my doubting of the Wild Duck Cluster that the image has changed. Ah. Does anybody see the wild ducks? I see a couple nods, and honestly, props to you. So, as I said, the Wild Duck Cluster is about 6,000 light years away. On a galactic scale, that's not so far. But remember, the closest star to the sun is about 4 light years away. 6,000 light years, much further than that. Still within our galaxy. The age of the Wild Duck Cluster is estimated to be about 316 million years, which sounds like a lot, right? But galaxies can live for billions of years. Stars can live for very, very long times, billions of years as well. So this cluster of stars at a few 100 million years old really represents a population of relatively young stars. It is one of the most compact open clusters at about 95 light years across from end to end. So again, you turn on a light at one end of the Wild Duck Nebula. It takes about 100 years for that beam of light to get to the other side. They're really very tightly packed together in space. Even though there are only even though the cluster, is only about 95 light years across, there are about 11,000 solar masses worth of stars. That's about 11,000 times the mass of our sun. Now, that doesn't necessarily mean 11,000 stars, because many stars are much more massive than our sun. Some are even less massive than our sun. But still, it's a lot of material. It's a lot of stars in a very small amount of space, though not quite as tightly packed as a globular cluster. Thanks very much, Bruce, for the view of the wild duck. Oh, is this a live wild duck, Bruce?
I think it is. I just can't tell where it's from.
Oh, so we have a live wild duck, we think, but we're not sure where it's from.
We prefer wild ducks to dead ducks.
We do prefer wild ducks to dead ducks. I'm not sure why that's where we went there. Yes, here it is. If the sky clears, there's a little bit of high-level cloud, it looks like. But later in the night, if the sky clears a little bit, then hopefully we will be able to see the Milky Way. It's a fantastic sight. I hope you get to see it tonight. So, we've talked about where stars live. That is in galaxies, sometimes in globular clusters, sometimes in open clusters. We talked about the different kinds of stars to some extent. And we talked about how stars were born. No. If anybody ever asks you what happens when a star dies, you can only give two kinds of answers. One is, it depends. One is, pardon? It depends on the mass, yes. So, you can either respond, it depends, or you can respond, a nebula. It is hard to go wrong with either of those two answers. As someone just contributed, what happens when a star dies depends almost entirely on the mass of the star. But whatever happens, you're generally going to get a nebula. So let's look first at what happens when a very massive star, let's say 10 times the mass of our own sun. So stars are burning hydrogen. Sorry, not burning, fusing hydrogen to create helium, to create heavier elements. In a very massive star, the star will fuse matter all the way up to iron. Once it gets to iron, it stops fusing because you get less energy out than you put in. It just doesn't work physically. When that happens, gravity takes over. Remember, stars are a battle between two forces, gravity and fusion. Fusion is causing the star to expand. If you're not doing any more fusion, gravity dominates and pulls it in together. But because the star has been fusing lighter elements into heavier elements, those heavier elements have sunk down towards the core of the star. So when gravity takes over, the star stops burning, the star suddenly collapses down and meets this hard iron, hard core, and just explodes. There's a word for this explosion of a star. I'm sure you know the word. Does anyone know it offhand? Does anyone remember? Supernova. The supernova is the term that we use to describe the explosion of a star. Does anyone know the origin of the term supernova? Great. If we knew all of the answers, I would be wasting my time up here. So, the word supernova originally comes from the term stellar nova, or new star. And the reason it was called a new star is because suddenly at night, or even during the day, there would be in this a new point of light that wasn't there before. Astronomers of all kinds have been tracking the stars throughout history, all across the planet, and would have noticed that something is there where it wasn't before. A stellar nova, a new star. We now know that this is what happens when a star explodes. It is an extremely violent, powerful event in space. It's the death of a massive star. So, what we have on screen and what has been on screen on and off for the entire presentation is an image of the Veil Nebula. The Veil Nebula is what's called, a supernova remnant. The Veil Nebula is the result of the explosion of a star that was about 20 times the mass of our sun. At the center is the remains of that star. Meanwhile, the red that we see forming roughly a circle is the result of the shock wave. All the material that was blasted off of the core of the star when it exploded, interacting with the gas around it. And as that shock wave interacts with the gas around it, it causes it to heat up. And once again, we have excited hydrogen giving off this red glow. The Veil Nebula is about 50 light years across. We talked about the Wild Duck Nebula, which was about 95 light years across. So this one supernova remnant, the remains of one exploded star, is about half of the size of the Wild Duck Nebula. Imagine a star going off in a dense cluster like that. What kind of views must that cause? I wouldn't want to be there personally, but it'd be great to catch on camera. And the Veil Nebula is about 24,000 light years away. So again, it's in our galactic neighborhood, but not immediately adjacent to us. So, what happens when a star dies? It depends. Fantastic answer. Or, what else can we say? A nebula. So, if a massive star dies, we get a supernova and a supernova remnant like the Veil Nebula. What if it's a much smaller star, something around the mass of our sun? Well, smaller stars don't burn all the way up, don't fuse, that is, all the way up to iron. They fuse hydrogen into helium, helium up to carbon. That carbon starts to form a core of the star, sinks down to the center. And when the star eventually runs out of hydrogen to fuse, it starts fusing helium. The star swells up, and then eventually those outer layers fizzle away when the star can no longer fuse. And as that gas flows away from the center, what's left behind is what's called a white dwarf. White dwarf is not a star in the sense that it's doing fusion, but it's still a very hot, very dense piece of material. It is the carbon remains of the star that has died. It's lost its ability to do fusion. It's lost a lot of the material that it would fuse. But it's going to be burning for billions of years because it's just so extremely hot. But we get a very dramatic picture because of that gas that flows away, that bubbles away from the center of that dying star. And what we call that is a planetary nebula. So the team is ahead of me, showing an image of what looks like the Dumbbell Nebula, M27, for those of us who prefer the catalog names, not me. But the Dumbbell Nebula is a planetary nebula. It's about 1,300 light years away in our galactic neighborhood. It's about 3 light years across. It is much, much smaller than the Veil Nebula, that supernova remnant, which is about 50 light years across. This is much smaller at about 3 light years across. It's about 10,000 years old. So there would have been humans looking up at the sky when the star died, but they wouldn't have seen the same stellar nova. They wouldn't have seen the same new star that we would see with a supernova explosion. So, last time, what happens when a star runs out of fuel? It depends. So, we've talked about where stars live, we talked about galaxies, we talked about globular clusters and open clusters, we talked about the nebulae where stars are born, and the nebulae that are caused when stars die. This is just really scratching the surface of the star's life cycle. Stars go through all sorts of changes in their lives. Even our sun goes through a process every 10 or 11 years of activity. So, call to action tonight. Go home, take what you learned here, and look into how stars live their ordinary lives. You'll find some really interesting things. And hopefully you get a better view of some stars tonight, if it clears up. I want to thank everyone here for being a fantastic interactive audience. Thank you so much. Quite a round of applause for yourselves. And I really want to thank the teams at ICO and at the Harry Bayley Observatory for fantastic work in providing us with some images. This was really an ambitious project. We're really glad that it came together as well as it did. I'm going to pass us back over to Kate now. I want to thank you again. Have a good night, everyone.
Thank you so much for that incredible presentation, Seneca. I don't know about our audience here, but I learned so much that I didn't know before about the life of stars. And I'm so grateful to you for being here this evening and for taking on this incredible challenge of not only interpreting the night sky to our visitors here in Killarney, but to visitors all over who are watching the live stream on the Allan I Carswell YouTube stream right now. So Seneca, thank you so much for this incredible presentation. Can we give Seneca one more big round of applause, please? I would also like to extend a huge thank you to our colleagues at the Allan I Carswell Observatory and the Harry Bayley Observatory for their participation in our program tonight. We wouldn't have seen all of the incredible views of some of these objects without their help and their participation this evening. So can we also give our colleagues there a little round of applause? And of course, thank you to our observatory founder, Bruce Waters, for manning all of the technology in the dome tonight to make sure we had these incredible views and for orchestrating this evening. So thank you very much, Bruce. And of course, I would just like to reiterate Seneca's thanks to all of you for attending this evening, both our visitors here in Killarney and our viewers on the live stream. For our visitors here in Killarney, if you're sticking around tomorrow night, Seneca is doing one more program with us while he's here at 7 p.m. at the amphitheater. He'll be doing a talk entitled Nature's Astronomers, Our Sky and the Living Planet. So I hope to see many of you there. And thank you all so much for coming out this evening.
All right, everyone, that was our official live stream tri-observatory extravaganza. I hope you've enjoyed it. The Harry Bayley Observatory has just had some clouds roll in. The Killarney Provincial Park Observatory remains clear, but they're stopping their wonderful talk. Oh, that was Seneca Smith from the Harry Bayley Observatory out at Killarney giving that talk, just in case you missed it earlier. And of course, the Allan I Carswell Observatory hosting this event did get pretty much completely clouded out. So I'm ending this live stream with a little view of the clouds. And one of the great things about having friends to work with is that if it is cloudy where you are, sometimes it's actually not cloudy where they are. So despite the fact that we had too many clouds to safely open the 1 meter domes, as seen here on the Allan I Carswell Observatory all-sky camera, now we had two other observatories who weren't clouded out. So you saw some stock images from Toronto, you saw some live images from Killarney Provincial Park in Ontario, and you saw live images from the Harry Bayley Observatory over in Barbados. Now, if you've enjoyed this program and would like to find out more about where Seneca Smith is actually right now out at Killarney Provincial Park, he is acting as the astronomer in residence this summer. The Astronomer in Residence program is run with the Allan I Carswell Observatory and Killarney Provincial Parks Observatory out in Killarney, Ontario. Now, the Harry Bayley Observatory joining in just made it a perfect trifecta. If you'd like to find out more about the Astronomer in Residence, how to join them on site at Killarney Provincial Park, or just to read their blog, which has live updates, that's yourq.ca/science/observatory/air. Now, if you'd like to join us this weekend, August 29th, we are also having a special Astro Fair on the Saturday, our 2026 Astro Fair at AICO. It is a fundraiser, and it will have an Astronomer in Residence station, which will feature both Bruce Waters and Seneca Smith, who you heard give the wonderful talk today. Thank you, everyone, for joining us for this tri-observatory adventure. Hopefully, it is the first of many. Clear skies, and have a good night.